move on to partial differential equations, let's look at, and I just want to briefly discuss some additional methods for ODEs. These are methods that are commonly used in various software packages, as I'll mention, including MATLAB and Python, but they do not extend to partial differential equations. I'm only going to discuss them very briefly and qualitatively in this video before we move on to PDEs. So if you remember, when we first started out on this, we were looking at two sets of classifications: single-step and multi-step methods, and explicit and implicit methods. And so far, everything we've done are single-step methods, meaning we know what happened at the previous time step, and we are getting the solution, computing the solution for the next time step. So a single step, meaning single time step method. And then within that, we had explicit methods and implicit methods, and you'll remember the advantages and disadvantages of each. So explicit methods are only first order accurate, so we have first order explicit, first order implicit method, but the explicit method is only first order accurate. It has poor numerical stability properties, which is its biggest issue, but they're very easy to implement because the equations are explicit. You just do the calculation and it's done, and they don't require any special treatment for nonlinear differential equations. So very easy to implement, easy to extend in nonlinear equations, but they're first order accurate and often conditionally stable in terms of numerical stability. Implicit methods, on the other hand, can be extended to second order accuracy. We did that with the Crank-Nicolson method, and they improve dramatically on numerical stability. So both the implicit methods that we discussed were unconditionally stable. However, the price you pay for that is there's more computation per time step than explicit methods, and it's difficult to implement for nonlinear equations. So as you can see, there's various trade-offs for each, and depending on the problem you're solving may point you to one or the other. So if we could be so bold as to develop a IVP wish list, so what would we like to have in a numerical method for initial value problems? The first is we want to maintain the favorable accuracy and stability properties of implicit methods. So that's why implicit methods are generally more popular than explicit methods, because of those two reasons. But if we could keep the ease of implementation and ability to adapt to nonlinear equations of explicit methods, then we'd have a perfect method, so to speak. So there are two types of, or two classes of methods that do this. One is called Predictor-Corrector, the other is called Multistep Methods, and they both are exactly what they sound like. So the Predictor-Corrector methods, they consist of two steps. So the first step is to predict the solution at the next time step. So you have the solution at the previous time step, and you predict using a standard explicit method the solution at the next time step. But instead of just moving on, as you would with a standard explicit method, you first correct. So you predict the solution at the next time step, and then you correct that solution. The prediction is using explicit methods, and the correction is using an implicit method. So it gives you a more accurate solution than at the next time step. Multi-step methods are very different. So they take advantage of the fact that we've already computed a number of time steps leading up to the next one that we're calculating. So single-step methods, we only use the solution at the previous time step. Why not use solution at multiple previous time steps? So those are multi-step solutions. And so we can take advantage of that to mitigate some of the issues that have arisen in the simpler methods. So again, I'm just going to look at a brief overview of these because they do not extend to PDEs, but they are very important and widely used in the ODE context. The simplest predictor-corrector method is Hume's method, and it builds on two of the techniques that we've already developed. The first step, the predictor step, we use the first order explicit method to predict the solution. Now we're going to put a hat on the variable u, so it's going to be u hat, because it's an intermediate solution at the next time step. It's not the solution at the next time step. So this is precisely the first order explicit method as we had before. The only difference is now we're just going to recognize that this u that we're getting at the new time step, un plus 1, is just an intermediate. It's just a prediction of that solution. In the corrector step, we use Crank-Nicolson to correct the predicted solution u hat at the next time step. So here is the Crank-Nicolson equation with one major difference from what we had before. That difference is, you'll notice that the u hat n plus 1 term is now on the right-hand side because we know u hat. Before, this term was on the left-hand side. We had to solve for it implicitly because we did not know u at n plus 1. But now, because we have the predicted value, we can put it over on the right-hand side. And now we have an explicit expression, even though it's Crank-Nicolson, we have an explicit expression for the solution u at the next time step. So that's Hume's method, very simple, builds on techniques that we already have in our toolbox. The most widely used methods for solving ODEs, initial value problems, are RungeKutta methods. It's really a class of methods. There's a whole bunch of these. And it's a predictor-corrector type method, but allows for higher order accuracy. So you can go to as high accuracy as you want in the way that we'll mention using the techniques that I'll mention. The standard, kind of the sweet spot, is what's known as a fourth order or fifth order RungeKutta. Fourth order is the most popular, and it's just a trade-off between accuracy and complexity of the method. Okay, I'm getting ahead of myself a bit. So it's a predictor-corrector type method that we can extend to higher order accuracy. So unlike predictor-corrector methods that I just described, RungeKutta methods involve function evaluations in between the time step. And depending on how many of those function evaluations you do at intermediate time steps between the two, n and n plus 1, that determines the order of accuracy of the method. So for example, a second order RungeKutta method would require one additional function evaluation at the midpoint between the previous and the current time steps. If you go to higher order, again, more of those intermediate calculations. They're usually only conditionally stable, so that seems like it's going backwards from the implicit methods, but usually the conditions are much less restrictive than they are for the first order explicit methods. So typically, you do have to keep in mind those restrictions, but typically the time step that you need for accuracy is sufficient to provide a stable solution. So there is that issue, but it's usually not nearly as bad as it is for the first order explicit method. As I've suggested, this is very widely used in general purpose initial value problem algorithms. The most popular version is the fourth order RungeKutta. Sometimes you'll see it as RK or RK4. For example, MATLAB, you may have heard of or seen ODE 45. ODE 45, actually the 4 and the 5 correspond to fourth and fifth order RungeKutta methods. So these are workhorses of ODE solvers that you'll find in various numerical packages. Multi-step methods, again, the whole idea is rather than throwing away all the information at previous time steps as we go to the next time step and only using the first previous time step, we can keep the solution and use the solution for multiple time steps. There are two basic approaches. One is explicit, one is implicit, and the explicit methods go by the name Adams-Bashforth, and the implicit methods go by the names Adams-Moulton. One of the issues with multi-step methods, and I hinted at this in an earlier discussion, is that you now do need a starting method. So a single step method where you start at t is equal to 0, move forward to n is equal to 1, n is equal to 2, you don't need a starting method. So you can start right away using Crank-Nicolson, for example, in the first time step. In these multi-step methods, you only have, as you do the first time step, you only have one previous time step. You don't have multiple steps. So you can't use a multi-step method to begin with. You have to have a starting method, such as Crank-Nicolson or something else, to get you going, to build up enough previous time steps so that you're now ready to use the multi-step method. So that's one of the disadvantages. The other disadvantage is that you have to keep your delta t the same. So before, remember, we said we could change the delta t because you're only taking one step at a time. So there's no reason why the current delta t has to be the same as the previous delta t. Now they have to be the same. The delta t's have to be the same because we have multiple time steps and using the solutions. So there are some downsides to this. And I'm not going to go through all these details. You can read through these on your own. But just an example, there's a fourth order Adams-Bashforth method. So Adams-Bashforth means it's an explicit method, as we said here. So an explicit method. So you say, well, how does that compare to a fourth order RungeKutta? And so you can see some of the discussion here on that. So typically, again, the reason why I'm not going through these in details is because the RungeKutta method ends up winning in terms of stability, typically. Adams-Moulton methods, they are implicit, but they do have better stability properties than explicit Adams-Bashforth methods. So you can implement these in a predictor-corrector type format. So it's a two-step process: explicit predictor step, implicit corrector step, using the appropriate Adams-Bashforth or Adams-Moulton method. So once again, it takes advantage of the simplicity of an explicit method and the stability properties and accuracy properties of the implicit methods. Finally, again, these can't be extended to PDEs, which is why I'm not talking about them in any more detail. I just want you to be aware of them. You may hear of them if you look in the literature, or if you're using various methods, particularly RungeKutta, and it's very easy. You can just look on Wikipedia to get the details on those. And, oh yeah, so we have a Dilbert. This is actually a fun one. It has to do with coding. So it actually does have something to do with computational mechanics. So one thing you'll find, and you probably have found as you've gone through your problem sets, that some of which have involved some coding, if you have looked at classmates' codes, it can be quite illuminating. So you think, well, we're coding the same problem to do the same thing using the same technique, but it turns out everyone's code is actually quite different, and there's somewhat of an art form to good coding. So what they're talking about here is what happens when someone takes over someone else's code. So either someone leaves, an employee leaves, or whatever the case might be, it comes from another department. And so you take over that code, and you got to figure out what they've done. So what Dilbert's suggesting is that we have a code mocking. So the first step is you look at the existing code and you see whether it's any good. You know, is it efficient? Is it readable? Is it understandable? Or is it a complete utter mess? So they're discussing one such code mocking, and it ends up in some very dire consequences. All right, so from now we'll pick up, and we're not going to spend a lot of time on PDEs for initial value problems, but I just want to give you a sense for how these three techniques that we've emphasized, first order explicit, first order implicit, and Crank-Nicholson methods, extend to PDEs. We'll do that in the next videos.